All right, everyone, we are back and we are going to now answer a critical question, which is sometimes we want to know what is the strain on a certain plane of interest. So, for example, if I have a truss, right? So I have a truss and there's some different systems like this and it looks like that. Like if I want to know when I exert a stress here, what is the stress at some particular orientation, for example, at some angle here, what is the actual stress state, not in this coordinate system per se, or we can actually look at this coordinate system, but what is the stress oriented in some new coordinate system instead of x and y? You can do, for example, x prime, y prime. What is the stress at some new orientation at some arbitrary theta here? So we need to be able to rotate our stress states to new coordinate systems. So you can do that. You have the skills. So you can use your concepts of static equilibrium. You can do and resolve, for example, here, if I have this stress state applied to my system, I could resolve all those different stresses, sum them all to zero in the new x prime direction, the new y prime direction, and then the new tau xy direction. So you can do that. I am not going to go through and look at all those tricks. And again, I don't think it's feasible to actually be able to do this in real life. But let's take an example stress state, and let's actually see these are all the stresses in the new directions. Oftentimes, we are very, very, very interested in figuring out where are or what orientation or what are the values of maximum normal or principal normal stresses. So, or actually really maximum normal stresses. A principal stress state is one in which where I only have potential stresses along my diagonal. Everywhere else, the shear stresses are all zero. So this is an example of a principal stress state. Now, sigma 1, sigma 2, sigma 3, we know it's 1, 1, 2, 2, 3, 3. Those can be, some of them can be zero, some of them can be non-zero, but our maximum normal stress is sigma 1, which is greater than sigma 2, which is greater than sigma 3. So that's how we kind of, that's what we're kind of seeing here with this sigma 1, sigma 2 notation. So we need to understand, or we need to be able to communicate what are the largest normal stresses, and what theta will I achieve the stress state where I only have stresses along my diagonal. Now you may be asking, why is this important? Well, lots of materials fail, especially a lot of brittle materials fail when normal stresses are maximized. So a lot of ceramics, glasses, those materials will fail when normal stress is maximized. So we need to be able to understand where is this stress state where I only have normal stresses, so that I can avoid it if I'm working with brittle materials. You can also have right here, what is our maximum shear stress? And that is important for, obviously, if I have metallic materials which typically fail via shear, I need to know that value and make sure that we're good to go. So, fantastic. Now, for Mohr circle, before we get to Mohr circle, let's analyze this stress state here. And I want to answer the following questions. What are my principal stress state values? So sigma 1, sigma 2. So what are the values of the principal stress? What is the angle, theta, that allows me to get to principal? So I want to do 1. So what are my sigma 1, sigma 2? 2, what is the angle to get to sigma 1, sigma 2? I also want to know what is the max shear stress. What is the 4? What is the angle to get to max shear? And 5, I want my new, basically, I'm gonna switch here from instead of my new sigma 1, 1 prime, my new sigma 2, 2 prime, my new sigma 1, 2 prime, because those are the only stress states here. And here we are in a plane stress state. All of this these equations that we're about to introduce only holds for plane stress state. So it's plane stress because I only have stress in one plane. Specifically, this is 1, 1, 2, 2, 1, 2. This is a 1, 2 plane stress state. So I only have stress contributions in the 1, 2 plane. So this is plane stress. So I want to answer what are my new stresses if I were to do a 15 degrees clockwise rotation around the 3 axis. So, very good. Or basically it's saying just rotating it in the plane. And we're doing clockwise rotation. So you can kind of visualize and see that same. Here you can just see this is basically my 1, 2 plane, and I'm going to rotate it clockwise 15 degrees. Well, I have lots of equations in here, so let's try to solve each of these questions with the plug and chug approach. So I am going to do, this is basically rewriting all of these equations here. So again, this is my maximum normal stress, minimum normal stress. This is my maximum tau xy. This is my theta p, which is where my normal stress is maximized, where I reach my principal stress state where there's only normal stresses. And then these are all my new stresses. So I can simply go ahead and plug and chug in here. So I could find, again, I have to input my old stress in the x, old stress in the y, old stress in the xy, or the 1, 1, 2, 2, and 1, 2. So I'm just plugging in the values here. So sigma 1, 1, sigma 2, 2, sigma 1, 2. So I could find, this is my maximum normal stress in the principal normal stress state. So my principal stress state, which is where I only have normal stresses. I can also do tau xy is going to be our maximum shear stress. So 6.4, as you can see here, we'll shift enter. Theta p, so I need to do to reach my maximum normal stress rate, I need to do a 19.33 counterclockwise, because remember, counterclockwise is positive, counterclockwise rotation from my original stress state. And if I were to do a clockwise rotation, I'm going to go here, here, here. This would be my new sigma 1, 1, my new sigma 2, 2, then my new sigma 1, 2. Now, these are correct. We were able to answer almost every problem except this one. We don't really have an equation that's just built in for us. Now, we can solve it. We could figure that out. And you could do some more rearranging for the values. But, and actually, what you could do is you can take the derivative and figure out what's the angle to get to that maximum shear. So we could, in fact, for example, we can take, so for example, tau xy theta, and we can do stress, we can copy this whole thing, actually. Except we need to do, this is going to be theta. And so I'm going to take the derivative of this with respect to theta. Oops. And then we're going to solve. Let me maximize this. Because I'm going to find at what angle is that value maximized. Solve when is equal to 0 in terms of theta. So we're given basically two answers. And we can actually pull this out. You can see this is one answer here. This is another answer right here. And we'll come back to these because this will be very important in a bit. So I can actually do a clockwise rotation. So for example, if I plug in here this value, and you see they're just related by 90 degrees. It's just a pi over 2 rotation. I believe so. So if I plug in this here, I'm going to get 6.4, which is equal to my maximum value here. So you see that that angle of basically a clockwise rotation of 25.6 will give me that maximum. So I can still use these equations to solve every item that we were required to do so here. Now, can you feasibly actually do this and remember these equations and, and plug and chug many times on a job interview. No. There's not a lot of intuition when we're solving with that plug and chug approach. So I would say it's not good that when you just plug and chug randomly, and you don't have any intuition on what's happening. So I would say let's not do the plug and chug approach. Instead, let's learn about a graphical approach that can actually allow us some more intuition in terms of solving, and will guide us to, I think, one of the best approaches is the linear algebra approach. So we'll see you then in the next video. Thanks.